I'm Dr. Sreelakshmy Kammath K S, and today the topic for our discussion is dental polymers. Synthetic resins or polymers refers to a molecule that is made up of many, that is poly, parts, mers. These subunits or mers represent the simplest chemical structural unit capable of conforming to the infinite number of configurations with entirely different physical and chemical properties. Terminologies. Monomer, a chemical that can undergo polymerization. Any molecule that can be bound to a similar molecule to form a polymer is known as a monomer, while a chemical compound consisting of large organic molecules built by repeating small monomeric units is known as a polymer. Polymerization, the formation of a compound by the joining together of molecules of small molecular weights into a compound of larger molecular weight is known as polymerization. Now that we are familiar with the terminologies, let's move on to ideal requirements. Ideal requirements will be discussed under biological, physical, aesthetic, manipulation and economic. So let's see the biological requirements of polymers. It should be tasteless, odorless, non-toxic, insoluble in saliva, non-irritating and sets quickly. The physical requirements are: it should have adequate strength, it should be resilient, it should be resistant to forces, and it should have adequate dimensional stability. The aesthetic requirements being: it should have color stability, it should be translucent or transparent depending on the area of use, and it should allow pigments to be added, either external or internal. Manipulation, it should be user friendly, it should be easy to mix, shape, cure, and it should be also easy to be polished and repaired. Economic requirements being: it should have a reasonable cost and no need for extensive equipments. Classification. Based on source, polymers are classified into natural and synthetic. Based on the thermal behavior, they are classified into thermoset and thermoplastic, with thermoset being no change if there is any increase in thermal energy, while thermoplastic means as the thermal energy increases, the material becomes more flowable, and as the thermal energy decreases or as the temperature decreases, the material becomes harder. Based on polymerization, the polymers are divided or classified into addition polymerization and condensation polymerization. Based on architecture, they are classified into linear, cross-linked and branched. Based on the microstructure, polymers can be classified into crystalline and amorphous. Crystalline being an orderly arrangement of all the monomers, while amorphous meaning a random arrangement. Based on the chemical composition, polymers are classified into homopolymers and copolymers. Homopolymers having similar mer units repeating, and copolymers having different types of mer units, monomer units. Copolymers are again classified into block, graft and random polymers. So we already said the polymerization is the formation of a compound by joining together of molecules of small molecular weights into compound of larger molecular weight. Polymerization occurs through a series of chemical reactions by which the macromolecule or the polymer is formed from a large number of molecules known as monomers. This can be either addition or condensation polymerization. Moving on to condensation polymerization. When two molecules react to form a large molecule with the elimination of a smaller molecule such as water, alcohol, ammonia, that is, we have a byproduct there, it is known as a condensation polymerization. And here in the example, you can see carboxylic acid react with amine to give you an amide and water as a byproduct. Such polymerization are slow in process and they follow a step growth polymerization pattern. The polymers formed will be of low molecular weight. This is another example of a dicarboxylic acid reacting with a diol, and we are getting a polyester as well as water as byproduct. Moving on to addition polymerization. Here, the reaction between two molecules is to form a larger molecule by addition reaction without formation of any byproducts. It starts from an active center and adding one monomer at a time to rapidly form a chain. This is also known as a chain growth polymerization. It is very fast and exothermic. It has high molecular weight polymers as the resultant, and molecules are added sequentially to the end of the growing chain. Here you can see an example of the same. Now, how does this occur? Starting from an active center, one molecule at a time is added and a chain rapidly builds up, which can grow almost indefinitely along as the supply of the molecules are available. It's only when the supply of the molecule stops, this reaction stops. So moving on to the chemical stages of polymerization. Chemical stages of polymerization can be described under four main headings. The first being induction, second being propagation, third is the chain transfer, and the fourth is termination. Induction or initiation period is the time during which the molecules of the initiator become energized or activated and starts to transfer the energy to the monomer. The initiator molecules become energized and break down into free radicals. The free radicals then interact with the monomer molecules to initiate a chain growth. The increase in temperature can result in rapid formation of free radicals, and this shortens the induction period. Activation. The free radicals can be generated by activation of the radical producing molecule using several means, most commonly heat, chemical or light. Accordingly, such polymers are termed as heat activated, light activated or chemically activated. Coming to initiation by heat. Most denture-based resins are polymerized by heat activation, producing two free radicals which then initiate and propagate the polymerization. Chemically activated polymers system consists of at least two reactants that when mixed together undergo a chemical reaction that generates a free radical. Light activated polymers, photon from a light source activate the initiator to generate free radicals that in turn can initiate the polymerization process. Here in this example, you can see a compound AB is split into A free radical and B free radical. Moving on to the next step of chemical stages of polymerization, which is propagation. The resulting free radical monomer complex acts as a new free radical center, which is approached by another monomer to form a dimer, which also becomes a free radical. The process continues with optimal velocity along with evolution of heat. As the initiated molecule approaches other molecule, the free electron interacts with the double bond of the molecule and a longer free radical is formed. This continues until the growing chain collides or all the free radicals have reacted. This is the example. Chain transfer. In this process, the active free radical of a growing chain is transferred to another molecule and a new free radical for further growth is created. Chain transfer occurs when a free radical approaches a methyl methacrylate molecule and donates a hydrogen atom to methyl methacrylate molecule. This causes the free radical to rearrange and to form a double bond, and that becomes unreactive, and the methyl methacrylate monomer to form a free radical that can participate in the chain propagation reaction. Chain transfer is a termination reaction also, by which the free radical site of a growing polymer chain is transferred to another molecule. The newly formed solvent or monomer radicals may then reinitiate the chain growth by resumption or propagation reactions. Termination. Although chain termination can result from chain transfer, addition polymerization reactions are most often terminated either by direct coupling of two free radical chain ends, exchange of hydrogen atom from one growing chain to another, collision of a growing chain with an initiation radical, collision of a growing chain with inhibitor. Inhibition. Any impurity, if it is present, it reacts with the monomer and inhibits polymerization. Example, hydroquinone, eugenol, oxygen, etc. An inhibitor aids in prevention of polymerization also during storage. In case of two parts, like in a self-cure system, it provides adequate time for mixing and placement of the material. Types of addition polymerization. We have free radical base, that is based on opening of the carbon-carbon double bonds and forming to joining to form a single bond based reactions, or we have ionic or ring based reactions where the ring opening reaction in which a 3-atom ring is broken open and then it joins with another broken ring to form a single bond. Both types of addition polymerization reaction also occurs. We talked in brief about copolymers. Copolymers are nothing but polymers which have two or more chemically different monomers, each with some desirable property that can be combined to yield specific physical properties of a polymer. Copolymers can be classified into random, block, graft, or branched. Random copolymer. In this, the different monomers are randomly distributed along the chain. In this example, you can see B type of monomers and A type of monomers. They are not following any order. They are just randomly distributed along the chain. A graft copolymer. In this, the sequence of one of the monomers are grafted onto the backbone of the other monomer species. Like it is joined. You can see a base polymer of A monomers as the main polymer, and you can see graft homopolymers of B, or a graft copolymer of B and C, graft homopolymer of C, etc. being attached onto the main base polymer of A. So these type of polymers are known as graft copolymers. Block copolymer. Here, identical monomer units occur in relatively long sequences along the main polymer chain. That is, you have a sequence of say 10 A type of monomers followed by 10 B type of monomers, etc. So to summarize, we can have copolymers with alternating monomers like AB, AB, AB systems, or you can have block like AAA, BBB, AAA polymers, or you can have randomly arranged like AB, AAA, BB, AB, like that. Any type of combinations can be available, and then we can have graft copolymers with a main monomer base polymer and another either a homopolymer or a copolymer getting attached to the base polymer, which is known as a graft polymer. What is cross-linking? The formation of chemical bonds or bridges between a linear polymer is known as cross-linking. It forms a three-dimensional network. It improves the strength, resistance to crazing, and decreases solubility and water sorption. You can see a cross-linked monomer will have more strength and resistance to crazing. So where are the polymers applied in dentistry, or what is the application of polymers? Do we use it regularly? Is it needed in our day-to-day life? Yes. We have dentures. The acrylic is made out of polymers. Impression materials, restorative materials, obturation materials, equipments. So these are some examples. The denture, the heat cured acrylic acts as the flange. The teeth is made out of polymer. Then you have impression materials like your elastomers, your addition silicons, these are polymers. We have gutta percha, your root canal sealants, your root canal filling materials, obturating materials, these are also polymers. Then you have your restorative materials like your composites, these are also polymers. And then you have equipments like the spatula that we use to mix the alginate, the bowls that we use normally for mixing alginate, or even plaster of Paris, all these bowls are also polymers. So this is your PCE for today. List the steps in chemical stages of polymerization. As an assignment, you have to draw and explain the various copolymers. So this is the learning outcome. That is, today's class basically described what the polymer is. It described a terminology, and then in detail we talked about the ideal requirements, the classification, about addition and condensation polymerization, about the chemical stages of polymerization, and about the types of polymers like the block polymer, the graph polymer, the random polymer, etc. Thank you.